The directions for all of these examples is going to be to solve for x. This example already looks like it's going to be pretty interesting for our domain, so let's do that first. In order to find the domain, we're going to take 5 minus 2x, and we're going to set that greater than 0. We need to solve for x. What do we do now? We divide both sides by -2. What do we get for the next line? X is less than 5/2. We need to remember that when you divide both sides or multiply both sides of an inequality by a negative number, you flip the inequality symbol. Domain would be from -infinity until 5/2, where 5/2 is not included. Here we have log base b of x equals y already set up, so all we need to do is change it to an exponential. B to the y equals x. 13 to the 0 equals 5 minus 2x. 13 to the 0 power, what does that equal? 1. Then we just finish up solving for x. Is 2 on our interval. Since 5/2 is really 2.5, and our domain is anything less than 2.5, and x is less than 2.5 when it equals 2, then our answer is good. The solution to our equation is x equals 2. What's the domain for this example here? All positive numbers. When we have log of a value minus log of a value, what property can we use to bring these two terms together as a single logarithm? We can use the quotient property. This will become the log base 5 of x over 3. It's still equal to 2. So all we did was implement quotient property. Now that we have a single logarithm, log base b of x is y, we can change it into exponential form. B to the y equals x. Five to the second is 25. Last step to get x alone. Multiply by 3. X equals 75. Is that on our domain? Yes. The solution to this equation is x equals 75. Again, having more than one log in the problem is not beneficial to us. We want to clean this up, pack this up down to a single logarithm. First thing we need to do is put this away. This needs to go back up in the exponent. That's the power property. Right now we're in expanded form of power property. We want to get it into simplified form. That rewrites this expression as log of x to the second power. This log has an invisible base of 10. Addition between two logarithmic expressions with the same base can be combined into a single logarithm using which property? Product property. This will become log base 10 of 4x squared is 2. Now that we have a single logarithm, we can go into exponential form because when x is in a logarithm, use an exponential equation. B to the y equals x. 10 to the second equals 4x squared. 10 to the second is 100. Divide both sides by 4 and we get 25 equals x squared. How do we get x alone? You have to take the square root of both sides. When you take the square root of both sides yourself in a problem, you're the one implementing it. It's important to remember you need to use plus minus. The positive and negative square root of 25 will give us plus minus 5. However, we should check our domain. Our domain is from 0 to infinity. So even though algebraically we were able to get positive and negative 5, the real final answer to this is just x equals positive 5. Negative 5 is not in the domain for this problem. It is what we call an extraneous solution. X equals 5 is the solution to this equation. What do we have here? This time we have x again in the exponent, and when we have x in the exponent, we use a logarithmic equation. We're going to take the log of both sides. What base should this log have? 8. Log base 8 of 8. We're just left with x. Log base 8 of 8 to the x leaves us with just an x. Log base 8 of 144 is a completely acceptable answer, and you could really leave it like this. If you wanted to be inventive, creative, and rewrite it a few different ways, you could. There's just too many ways to write this answer, so here are a few ideas. However, this answer is totally fine. You don't need to check your domain because x in the exponent has a domain of all real numbers. X in a logarithm does not. You always have to check the domain when you solve a logarithmic equation. I know we use log to solve this. However, we solved an exponential equation. We have our x in the exponent. We're solving exponential. We're going to use a log. We're going to use log base 3 on both sides. We need to get x alone. You want to multiply both sides by 1/7. Where you write the 1/7 does matter because you don't want to make any mix-ups. Either of these is acceptable. After we learn the change of base formula, you're going to see a lot of these answers that we are solving right now could be rewritten in a few different ways, but I wanted to stick to one thing at a time. We want to clean this up into a single logarithm. We're going to do that by putting our coefficients up into our exponents. Which property are we going to use now that we have subtraction between two logarithms? We're going to use the quotient property. 2 to the 4th is my numerator, which is actually 16, and x to the 2nd is my denominator. Now that I have this written as a single logarithm, I can rewrite it in exponential form, because when you're solving for x, and it's in a logarithm, we use an exponential equation. 3 to the 1 equals 16 over x squared. 3 to the 1 is obviously 3. 3 equals 16 over x squared. That 3 is really over 1. 3x squared is 16. X squared is 16 over 3. Now let's go and pause for a second. What's the domain for this example? X has to be greater than 0. So the domain is from 0 to infinity. We're going to continue solving this problem over here. We're going to take the square root of both sides. We start with the plus minus. Square root of 16 is 4. Square root of 3 is square root of 3. We need to do something about this denominator. It's called rationalizing the denominator, because radical 3 is an irrational number. We got two answers, positive 4 root 3 over 3 and negative 4 root 3 over 3. Since we just said our domain is only positives, we're going to have the negative be our extraneous solution. So the solution to this equation, the only actual solution, is the positive 4 root 3 over 3. We do not need to write the plus sign in front. It is implied when nothing is written. The base of a logarithmic equation, where we have the natural log, is e. It's already isolated. You can go from logarithmic to exponential form. E to the 6 is 3x. Getting x alone means we multiply both sides by 1/3. So we can leave it as 1/3 e to the 6th equals x. Or maybe we write it as e to the 6th over 3. These are the same answer. Here we have the natural log again, base e. I'm already in the form, log base b of x is y. Go to our exponential form, e to the 8th. You don't need a calculator. This is more precise and accurate. It's exact. e to the 8th equals 2x plus 3. You can write your final answer in a few different ways. One way is e to the 8 minus 3 over 2. Another option would be with the 1/2 out front, e to the 8th minus 3. E to the 8th power is a pretty large number. Minus 3 over 2 is going to be a positive number. Even if we don't check our domain, there's no way I'm going to get a negative number inside this parenthesis. Whenever we check our domain of log, we're always just making sure that we're not going to end up taking the log of a negative number or the log of 0. Neither of those works. If we did want to find the domain, it's all numbers greater than negative 1.5. Definitely greater than negative 1.5. Here we have another situation when x is in the exponent, and we're going to have to use a logarithmic equation. The base of this exponential is e, which means the logarithm will be ln. Before we can do that, we need to subtract 4 from both sides because we need to get our base to a power alone. Now that we have e to the x over 5 equals 3, we can take the log base e of both sides. Log base e is ln. The ln and e are inverse operations, just like log base 2 and 2. To undo the divide by 5, we multiply both sides by 5. X equals 5 ln 3. Here's the last example. We still need to get our logarithm alone. We're dividing both sides by 2. ln of 2x squared equals 1/2. Don't forget the ln has a base of e. We can rewrite this from logarithmic form to exponential form because when x is in a logarithm, we use an exponential equation. E to the 1/2 power equals 2x squared. We can leave this as e to the 1/2 power over 2. We can write it as 1/2 in front. I'm going to leave it like this time. When you want to get rid of an x squared, you just want x. We often say we take the square root of both sides. But recently, we went over what power a square root really is. What power or exponent are you using when you take the square root? The square root is the same as the 1/2 power. 2 times 1/2 is 1, and then we're just left with an x. This is still technically a square root, so we do need a plus minus. E to the 1/2, all raised to the 1/2, you multiply your exponents, that's really e to the 1/4, which is actually the 4th root of e. this 1/2 power, or square root, is really being applied to that 2 also. So it's really a radical 2 in my denominator. We rationalize our denominator. X equals 1/2 e to the 1/4 or 4th root of e square root 2 over 2. Since our x in our equation for our log is being squared, if I square a negative number, I'll get a positive number. The domain for this problem is everything except 0. Every other number will make this inside positive. If you think about it, this is a parabola. 2x squared is a parabola narrow at the origin. It's never negative. It's 0 at when x is 0, but neither of these numbers is 0. Both of these solutions will work. Hope you like these examples. Hope that they helped you out. Hope that you wrote down these two main rules over here at some point. It's really what it comes down to for all of these problems. Good luck doing your homework.